In Chapter 12, we're going to take a look at box models, what they are and how they can help us in statistics, particularly with those tricky probability problems we've been working on so far. So to introduce you to the concept of what a box model is, I'm going to first give you a scenario that I encountered very frequently when I was a little kid. More often than not, me and my best friend would get into disagreements about what we should do that day. And so say I wanted to go to the park and she wanted to play a video game. In order to be fair is fair, we would always say, well, let's flip a coin when we couldn't decide and debate was getting us nowhere. So then we would both reach for our pockets looking for a coin, and sure enough, nobody would have any money on them. So the way that we were able to simulate a coin, the next thing that I would do is I would run over to the printer, I would grab a piece of paper, I would rip it up into two pieces of paper, and I would say, okay, I'm going to write on mine going to the park, and you're going to write on yours playing video games. We'd crumple them up, and we'd throw them into a box, or a hat, or somebody's pocket, or something. We'd shake it up so it's nice and fair, and then randomly draw one of the tickets to decide where we were going to go, or what we were going to do. What I had done, without knowing at the time as a little kid, was created a box model. I had simulated the probability of a fair coin. I was able to somehow take two tickets and imitate the probability of flipping a coin and having an equal chance of getting either side. Just like when we stuck our hand into the box, we had an equal chance of picking either ticket. So that's what I really want you to think about with a box model. Think about a physical box and think about actual tickets when I'm using those terminology. So let's dive in and try and translate this box, this physical box that I have right here, into a box that we might see on an exam or in our homework. So if I wanted to create a box model to simulate a fair coin in flipping a coin and getting ahead. So we're going to say, let's simulate a box where it's the probability of flipping a coin and getting ahead. There's our problem. So the first thing you got to do is draw your box. And just quite literally, draw a box. And inside of our box, we are going to have two tickets. And there they are, our very figurative tickets. And on one ticket, I might write head, or H, for what I want, because the goal is to flip a coin and get ahead. And what I don't want would be that tail. So I've written it with H's and T's. Now this is very helpful in real life when we're actually trying to simulate the probability of getting an actual head. But in statistics, we're more concerned with the numbers rather than with the figurative, George Washington's face on the coin, right? So instead, we're going to convert this box into something a little bit more useful for us. So because we are concerned primarily with the probability of that coin turning up as a head, we're going to instead call that ticket a 1. And the object that we are not concerned with, the object that gives us the outcome that we're not satisfied with this tail, we're going to count as a 0. And you might say, well, why 1s and 0s? Well, let's think about it a little bit closer. If I was going to, let's say, flip a coin 10 times, and I was going to add up the number of heads I get, as I was doing that, what would I do? I would basically keep tally. I would say, okay, here I am. Here are the number of heads. Flip a coin. Oh, hooray, it came up as a head. That's one head. Flip a coin. Oh, there's a second head. Flip a coin. I get my 3 heads in a row. Flip a coin. Let's say I get a tail. What do? I don't mark anything, right? I've been marking 1s for what I like. And when you're keeping tally, you mark it basically as a 0, or you don't mark if you get a tail. On the fifth flip, let's say I get a head. You mark another tally. 6th flip, I get a 0, a tail. You don't mark anything. The next flip, you keep going. So what you want, you're going to code with 1s. What you don't want, you're going to code with 0s. So that's the most basic box model, just kind of putting our toes into the water. So now let's take a look at a different box model. So now let's work on a problem that might be a little bit closer to home for where we are today in our collegiate careers. So, say that we walk into a multiple choice exam for a class that we've never gone to and we've never studied for, and we decide to wing it and just guess on every single question. We can create a box model to simulate the probability of doing well on this exam, or guessing the right answer on as many as we possibly can. So, a box model for this question where we have a multiple choice exam where on each question you have 5 choices, so A, B, C, D, and E. And only one of those 5 choices is correct. If we guess the right answer, we get a point. And if we guess the incorrect answer, we gain 0 points. So, to turn a lot of this language into actual numbers and figures that we can work with in statistics, we're going to once again draw our box. And inside it, we're going to mark it with 2 tickets. Why 2 tickets? Because there are 2 possible outcomes when we guess on each question. When I guess on this question, let's just say I'm simulating question 1 on the exam, where I have option A, B, C, D, and E. Say the correct answer is D. That means these answers would be incorrect. What I'm basically trying to show you is there's 2 outcomes. We could either get it right and guess the correct answer, or, oh, that's a smiley, or we could guess any of these other ones and get the answer wrong. So I'm going to condense my box model into 2 outcomes, getting the correct answer or getting the incorrect answer. And I'm just putting that down there just for my own sanity, the correct answer and the incorrect answer. So now, what do I want to write on each ticket? Well, what we write on the tickets are the actual values. Basically, what is gained or lost with that outcome. So, if I get the answer correct, what do I gain? I gain 1 point. So I might write +1 on that ticket. If I get an incorrect answer, what is gained? 0 points. So I would write 0 on that ticket. Now a lot of people might just stop here and move on to the next problem on their statistics exam because this is where we left off for the heads and tails. But we need to remember, we don't just have an equal probability of getting the question right or wrong. This isn't true-false. This is multiple choice. And as you can see, we have a lot more, there are many more ways to get the answer wrong than it is to guess it right. So underneath my tickets, I'm going to actually write the number of ways that that can occur. So the number of tickets, basically. The number of tickets. So on this exam, because there are 5 options and only one of those options is correct, I'm going to say there's only one way to randomly guess and get the correct answer. While you can see from over here, there are 1, 2, 3, 4 different ways to get the answer wrong. So I need to make sure that in my box, I have 4 outcomes that are worth 0, and only 1 outcome that is worth 1. And this should always add up to 5 because that is the total number of outcomes on one question. The most common mistake that's made on questions like this is students try and think too big picture. We want to first focus in on one individual problem, as if we're taking the exam ourselves. You noticed I started working on question number 1. We need to think about this as question 1 by 1 by 1. We have 5 options, one of them is correct. Then think about your values, what they're worth. Where the actual number of questions would come in handy is the number of times that we draw from this box. So let's say that this was a 50-question multiple choice test. So there are 50 questions on this multiple choice test. This box would still be the exact same. My box would be the same no matter how many questions. What changes is n, and n denotes how many times we pull from the box, how many times I grab a ticket from it. So we're going to say n is equal to the number of draws. So in this case, I would have this box, and I might say, n is 50 from this box. And this gives me a lot of information. And in the future chapters, we can actually go on further to simulate the outcome, what my most likely exam score would be, for instance, or how much error I can expect to have on my prediction. So I hope that this one makes a little more sense. It's a little bit trickier and not quite as intuitive, but let's keep moving. Now to make this problem a little bit more tricky, let's say that you had a slightly meaner teacher who instead of grading where incorrect answers were worth 0 points, instead they actually started deducting points for each incorrect answer. So let's say for every incorrect answer you would get 2 points removed from your score. How would my box model change? Well, I would still have 5 tickets in my box to represent the 5 possible outcomes that I could choose from. So I would still have 1 way to be correct, 4 ways to be incorrect. What changes here is basically the stakes, what's at risk here. So I still can gain 1 point for a correct answer, but now the value of my second ticket would go from being 0, which was basically no consequences, to being -2. So that's something that you might see on some problems and find a little bit tricky. So keep an eye out for that. Make sure you're very careful. Box models are not always 1 and 0 boxes. They could be any value. They could be denoted by the stakes listed in the problem. Now let's try and create some box models focused around dice, a common game that uses a lot of statistics. So making a box model based on dice is a little bit tricky because you can do a lot of things with dice. We could roll these dice and count up the number of spots. I could roll the die and count how many 4s I get, because that's a lucky number. I could roll the die and count how many even die I get. I can do a variety of things. So I want you to be wary. The problem can change even though it's surrounded by the same physical object. But so let's say, just to start things off, that I was concerned with summing up the spots on the die. So I roll a die 100 times when I'm bored on a rainy day, and I'm just adding up the number of dots I see. So we're going to say, we're just summing the spots. Okay? So we're going to start with our box. Now we need to figure out how many tickets to have in this box. Well, before I was dealing with heads and tails, right or wrong, how many options are there on one single roll of a die? That's what I wanted you to focus on. 1 pull from the box, 1 roll of the die. So when I roll a die, I have 6 options, 1 through 6. So I'm going to have 6 tickets in my box. So I'm going to redraw this to be a little bit friendlier to myself and say, there is my box. And inside my box, I'm going to have 6 tickets to represent each potential outcome. Things are getting a little wacky. Okay, there we go. So 6 tickets, 1 to represent each potential outcome on a single roll of the die. So on the first ticket, to represent the 1 dot, let's write a 1, and a 2 on this one, and a 3 on this one, 4, 5, and 6 dots. So I've translated these dots into the actual number of dots and put those on tickets. So now it just depends on what we want to do. If, say for instance, we rolled 100 times and we were summing up the spots, we would just be selecting tickets from this box and adding up as we go. So we could say, all right, I got a 2, and then I got a 5, and then I got a 1, and then I got a 6. That's basically what we'd be doing, summing up the sum of the spots. One thing I do want to touch on is that when we are rolling a die, when we're making our box, the question often comes up of, is this with or without replacement? And I want you to remember that a physical die is not going to change, right? After you roll it the first time, the probability isn't going to change for the second time. Otherwise, we would all be millionaires in Vegas. So, whenever you're dealing with a die, you're always going to consider this as with replacement. We're going to be putting these tickets back in the box after each roll. Because when you roll a 2 in die, it's not like that 2 suddenly burns off the face of the die, never to be seen again. Right? You still have a chance of getting a 2 on the second die. So always remember, when we're doing this, we would say this represents drawing from this box with 6 tickets, numbering 1 through 6. We would say n is equal to the number of draws, the number of times I'm playing the game. And then we would also say that this is, of course, with replacement. Same thing for a coin, same thing for the multiple choice test. Those sides of that physical object aren't going anywhere. So let's get to the reason you decided to take Stat 100 in the first place. Money. Vegas. Let's pretend that we're going to Vegas and we want to tilt the odds in our favor. One of the safest games to play on your next trip to Vegas is roulette, and you're going to learn a lot about roulette in the next few chapters. So, what is roulette? I sure didn't know before my life as a statistician began. So, what I recommend you do is Google roulette. Just to see this roulette wheel that I'm going to try and draw out so artistically for you. A roulette wheel is basically a big wheel that spins around. It has numbers like 9, 10, 11, 12. It has colors, reds, greens, blacks. And what happens is that you throw a little ball, it spins and it spins and it spins until it lands on a slot. So remember, the slots have colors and have numbers. So there's lots of different problems that can be made, and lots of different bets that can be made in Vegas. So, the most important points to know about your roulette wheel that you probably didn't know before this problem is that a roulette wheel has 38 possible slots for your ball to land on. 18 of them are red, 18 of them are black, and 2 of the very high stakes slots are green. And they are numbered from, I should write this down. They have numbers 1 through 36, and then there is a number 0, and there is a number 00. Those are the 2 green ones, just for future reference. So, say we were going to go to Vegas and we were going to play this low stakes game of betting $1, which is what I recommend. So we're going to bet $1 on red, and we're going to play 25 times. First of all, what this means, betting $1 on red, means that if we win $1. But if we lose, we also lose that dollar that we put on the table. So you win and lose the same amount. Those are the stakes there. Okay, so now we're betting on red. So if it lands on a red slot, we win $1. If it lands on any other slot, green or black, we're going to lose $1. So to turn this into a box model, I'm going to write this in terms of the outcomes I care about. Winning and losing. So those are the 2 outcomes that I really care about. So I'm going to have 2 tickets. So the values, let's talk about the values. If I win, I have the potential to win $1 each time. So that value is 1. If I lose, I can risk losing $1 each time. So there's the -1. Now the next question is, how many ways are there to win? Well, I'm betting on red, and there are 18 red slots. So I have 18 tickets that say +1, which leaves the 18 black and the 2 green against me. And there's the 20 losing tickets. And now you can see why the house is, the game is always stacked towards the house. Vegas wouldn't be open if there were equal shots of winning. So, here is our box model. Now we can do anything we want, and the last thing I'm going to say is that n is equal to 25. And of course, this is going to be another situation where we are dealing with replacement. Because this physical object, these slots aren't going anywhere after we've picked them from our box. So we need to replace each ticket each time that we play. So, just to make yourself just to get things a little bit more exciting, let's say instead of betting $1 on red, let's say that we decided to bet $100 on green. Okay? And just to make things a little bit more clear, let's say if you win, you can make these problems anything you want and anything that the dealer will allow you to make them. Let's say if you win $200, but if you lose $100. That's usually what that betting means, how much you're willing to lose. So the only thing that would change here, let's get rid of this, we still have the winning option and the losing option, but our chances are going to change this time. So if I win $200. If I lose, I stand to lose at -$100. How many ways can I win? Well, there's a reason this is so high stakes. There's only 2 winning tickets in my box, which leaves 36 losing tickets in my box. So you can see the fun that can be had by doing all of these problems, betting on different numbers, number combinations, colors, etc. So good luck with your pre-lecture questions, and have fun in lecture. Go win some money.